So I'm delighted and honored to introduce our first plenary speaker, Joelle Pineau. Joelle is a professor at Mila, which is a famous machine learning research institute in Montreal. In addition, she is a professor and William Dodson Scholar at the School of Computer Science at McGill University, where she co-directs the Reasoning and Learning Lab. She's also co-managing director of Facebook AI Research and the director of its lab in Montreal. I actually don't know how is that physically possible without having a couple of clones. So we're definitely lucky that Joelle found time in her busy schedule to give a talk here, or maybe send her one of her clones. Joelle works on developing new models and algorithms for reinforcement learning and has made many major contributions to this area. She also works on applications of these algorithms in robotics, healthcare, conversational agents, and games. Joelle has received numerous prestigious honors and awards for her work and holds several leadership positions in the machine learning research community. But I think you would all probably prefer listening to her instead of having me recite this long list. Today, Joelle is going to talk about the challenges arising when applying reinforcement learning algorithms in practice, as well as approaches to tackling those challenges. Please give her your welcome, your warm welcome.
Thank you. Thank you for the warm introduction. Thank you for the invitation. It's a pleasure to be here. I assure you, no clones needed. I was really delighted to spend some time with you today. Some familiar faces from the community, always really nice to catch up, even though we can't be in person for this. So just jumping straight, into the discussion for today. I think I've been in the field of AI for a couple decades now, and really seen the rise of interest, but also really the expectations coming with the development of the technology. And walking into this space where I walk a bit of a fine line between academia and between the industrial world, there's keen awareness sometimes of the gap that we see between the promises we hear about and what our methods are actually able to deliver in any time that I can, make reasonable predictions for. And I also, in many cases, see quite a gap between our understanding of these methods, these phenomenons from a theoretical point of view, and what we see in practice. So I will say a lot of my research has been driven not so much, perhaps eventually, but not so much by bridging that gap, but really by being cognizant of that gap and really bringing the best of each side to inform the other side. And so being really thoughtful about when we're making, practical applications of AI, how can we rely on our theoretical understanding to guide us in the numerous choices that we have to make? And similarly, when we're asking more theoretical questions, grounding the assumptions that we will make on the practice and on the potential deployment of AI. And so in that sense, I come to you today mostly as a practitioner of AI, but one that is keenly interested in leveraging all of the wonderful talents on the more theoretical side so that we can make some progress together in these conversations. My field of expertise is mostly in reinforcement learning. I jumped into reinforcement learning in the days of my PhD, seduced by the elegant mathematical framework of the model itself, the framework, as well as the algorithms that came with it. Over the years, I've been really interested in figuring out how can we apply reinforcement learning in practice to real-world applications. I will assume most people here with us today are quite familiar with reinforcement learning already. If perhaps you've missed it, I encourage you to dig in. Really quite interesting framework. It gives us a comprehensive way to train agents to predict when to choose certain actions, what will be the effects of these actions on the world. And really the goal is to optimize the behavior of these agents. So the sequence of actions that will yield a goal or will yield rewards over the lifetime of the agent. We've seen impressive successes in games on some of these reinforcement learning agents recently, whether it's the AlphaGo system a few years ago, showing that you could beat the best human player at the very challenging game of Go. The Libratus poker player, also really impressive results against human players of very, very high caliber. in some of these cases, these are applications of RL where we understand the rules of the games very well. Even in the language of the machine, we can describe the conditions for the decision problem in a relatively compact manner. It doesn't mean that searching for the solution is compact, but the description of the problem and its characteristics can be done in a relatively compact manner. And in a way that gives a lot of structure to solving those problems. What I'm most interested, though, I'm impressed and delighted to see the results we've seen in games, but what I'm personally most interested in is figuring out how we can take RL models, algorithms, and deploy them in real world application, in particular for healthcare. But I want to say a lot of what I'm talking about today, I think could be more broadly applied to any of these applications that I list over there. These are not hypothetical applications. These are actually applications I've drawn from recent papers at the RLDM conference, Reinforcement Learning and Decision Making. And there are people in our community actively working on all of these applications of reinforcement learning. And so I think, really the deployment and that exploration phase of what we can do with this work is really going much beyond games very, very rapidly. And as we take on the applications that are more driven with respect to healthcare, there are specific questions that arise in terms of the soundness of our approach, the robustness of our approach, and questions, of course, of safety. And so that's why my talk today is geared a little bit more towards these questions of safe and sound reinforcement learning. But at the end, I will broaden this up into other considerations and other characteristics that are important to take reinforcement learning systems into the real world. Speaking very concretely of a project we've done in applying reinforcement learning, just to ground you in an examples of work we've done a few years ago on developing a new treatment for epilepsy. Epilepsy is a disease that essentially affects about 1% of the world population. For most people, the first line of treatment is pharmacological. In some cases, the second line of treatment is actually surgical intervention, so resection surgery, where you take out a small portion of the brain where the seizures are emerging. For some patients, neither of these is a very good alternative. And so the third line of treatment is a technology we call neurostimulation, where there's a small device that's implanted, usually in the chest cavity, with electrodes reaching into the brain. And these electrodes are either sensing in real time the neural discharges in the brain, as well as stimulating, so delivering electrical stimulation to the brain in a way to abort the seizures. And so this technology has actually been tested and deployed in patients. There's different stimulation sites, different techniques, and so on, but this is a technology that is starting to be used in real patients. Speaking as a machine learning expert, most of the time I want to very early on in a project see the data, get a feel for what the data looks like. So in this case, we are receiving real-time EEG signals sampled at a very high frequency, around 100 hertz. And what we see here is an example of such a seizure in an animal model of epilepsy. So this ictal event is essentially the seizure. It lasts about 50 seconds or so. Before that, there's these characteristic spikes that you do see in epileptic seizures, both in human patients and in animal models. After that, there's usually a period where the neural activity really decreases. And so what I'm sharing with you is a little bit our understanding of the dynamics of the disease. But when it comes to using reinforcement learning, we have to find a way to translate this broad understanding of the dynamics of this complex system into a language that the computer will understand, and also into a set of assumptions, priors, constraints on our learning system. In this case, with respect to using reinforcement learning, the theory is that if you stimulate at particular time points, you can essentially prevent the neurons from all synchronizing. So the seizure occurs when all the neurons are simultaneously firing at a time point. And after a while, they've sort of exhausted all their resources to do so, and they go into a quiet period. And so neurostimulation, when you deliver that stimulation, the neurons around start firing at times that they didn't plan to do so. And so you're essentially preventing the recruitment of and the synchronization of all the neurons. So there's already a strong hypothesis coming from our partners in neuroscience that neurostimulation can be effective, what you'll notice here, even if you're not familiar with reading EEGs, is these spikes occurring at very regular interval, 1 second each. This is stimulation that is delivered on a 1 hertz frequency. And so this is one of the patterns that has been shown to be effective for this particular model of epilepsy. So looking at this again from my mindset of reinforcement learning, I at least have an initial policy, an action strategy that I know has been shown to be safe and effective. But I have this hypothesis that perhaps we could do a lot better. If we space out the stimulation differently, maybe you can be more effective at avoiding seizures more early on. And you can also be more effective at reducing the amount of stimulation, which can also be costly in terms of damage to the tissue. So when we set up this project initially, it looks like a reinforcement learning system, the one I showed you earlier with my agent. In a sense, my environment is this in vitro model of epilepsy. The advantage of having an in vitro model is that we can afford, at least in this early part of my talk, to not consider the safety constraints and really look at, can we learn this efficiently? So this is my environment. It's a dish where we've put a slice of a rat brain where we've induced epilepsy. The state is captured from the EEG signal. It gets fed to this laptop where we compute the policy. And out of this comes a command at different intervals of whether to deliver stimulation or not. And the reward function is composed of both a particular component for the seizures and a particular component for the delivery of a stimulation. So very classic reinforcement learning model in many ways. When we started working on this, we looked at a few different approaches. One of the ones we considered is a model-based reinforcement learning. There's a strong, message in the community. Model-based reinforcement learning can be sample efficient. We have some theoretical results to support this. They come with very specific assumptions, but still, there's certainly a lot of value when you can make some structural assumptions in doing that. And so we proceeded in building a forward model of the dynamics from the data we have. The data was recorded from 8 slices. So just give you just a taste of the scale of what we're working with, right? 8 slices, we usually record over a 4-hour period. After that point, the slice starts behaving very differently, sort of degrading in terms of quality. In the data we had, we were not able to control exploration. It's often the case with these kinds of problem. We got data that was recorded under a particular experimental protocol that the team was exploring. For another research question, we're sort of piggybacking on their experiment to even get access to this exploration data. In this case, over the 4 hours, they had separated into shorter periods where they will alternate from no stimulation to constant 0.1 hertz, no stimulation, 0.2 hertz, and so on. They'd sort of up the steps of the stimulation frequency interspersed with control periods of no stimulation. And when we build our forward model, what we actually found is we could to some degree reproduce the phenomenon that you're seeing. I'm showing you here both the original data as well as some predicted data that is from this model. So on the overhaul level, it actually looks reasonably similar, and including the response to different fixed intervention strategies. But for our colleagues in neuroscience, there's actually a large gap between these two types of data. And, they'd have to go more into details about what are the indicators they looked at, but they, their response when I show them this data is like, this looks nothing the same from a physiological point of view. And I really doubt that you can train an RL system from this forward model data. And so on the basis of many of these, much longer, I'm resuming in 20 seconds to the discussions we have over a period of several months, but we sort of pivoted back to trying a model-free reinforcement learning model. So it's just to give you an idea of, we have a very complex problem, and even diving into this, the hypothesis about what's the class of approaches that might be more successful changes in midway as we get to really understand the characteristics of the data, but more deeply. So in this case, we pivoted to a model-free method, fitted Q iteration. In this case, we learned the Q function. So the Q function is a predicted sum of rewards for a given state and action combination. We did that actually with random forests, which is like incredibly, classic machine learning methods. The main reason why we picked such a model is because they have very, very few hyperparameters, and this will come back in my story today. Very few hyperparameter and very stable to the misspecification of these hyperparameters. So when you have such small amount of data, thinking in terms of what's the budget for estimating your hyperparameter or for estimating any conditions of your model is absolutely crucial. And this is why we turned to this particular model. We spent about 6 months collecting the initial data. We spent about 6 months, really doing the training of the model. And then we literally had to cross our fingers, bring the laptop to the wet lab, and wait until they ran the policy evaluation. So for most people here who have done reinforcement learning experiment, right, the evaluation is the easy part. Right? You run millions of trials, you train your model, and then once in a while you pause and you evaluate, you run a few mazes or a few Atari games and you get your answer. In this case, we essentially got one test run. We had 12 slices planned for this in our budget. One of them did not react to the preparation in the right way, so we had to discard it. We were left with 11 slices. And from this, we had to show whether we were able to significantly improve either in terms of performance, so reducing seizures, or in terms of efficiency, in terms of reducing stimulation. And so fortunately for us, the bet did pay off. We were able to show that our stimulation efficacy was as good as the best known strategy, and that our ability to reduce stimulation was more effective. So there was an efficiency gain for this particular model of epilepsy. Moving forward a little bit, right, in a sense, this is a preliminary study going on to something more ambitious, and there's really a gap between the in vitro model and the in vivo model. And in our case, when we move to in vivo, whether it's animal or human models, there's no a priori knowledge of what's even a good policy to explore data from. There's not even a good sense of what's a class of policy that might be appropriate in this case. The difference between the seizures within a single individual are much larger. Over time, the disease evolves in a way that it doesn't in vitro. In vitro, we have 4 hours, it's pretty constant, then it degrades, but we stop right before that. We don't have that advantage in live models and animals. So much more complicated situation. At this point, let me sort of, pivot from my story on reinforcement learning and epilepsy and sort of bring this up to a higher level in terms of what we're trying to do here, and really go back to this early question. If we are convinced that we are using AI to improve our ability to deliver on really ambitious new use cases, improve the life of our colleagues, our families, the population around us. In healthcare specifically, we see so many claims of AI on its way to make the treatment of patients faster, cheaper, personalized, more accessible, more accurate, more comprehensive. And I think there's a really big responsibility that we bear as scientists, as researchers, to come up with good support anytime we're going to make one of these claims, and make sure that we are not claiming it for the purpose of a paper, but really thinking about the broader implications of doing that, and whether we have the credibility to claim that we can reliably achieve this. And it's always good to be inspired by some of our predecessors. In this case, Richard Feynman, I think, had this interesting quote, the first principle is that you must not fool yourself. And frankly, you are the easiest person to fool. And so that's a little bit my message as we are entering into this work. In my case of doing practical reinforcement learning, in some of your cases in the questions that you take on, really maintaining the spirit of rigor when you enter into any work that you are doing, whether it's more theoretical or more practical. One of the measures of rigor is whether the work that you produce is reproducible, let alone my question of, can we go from our in vitro model to a live animal model? If I do a study within one model, one set of constraint, one data set, could someone else actually reproduce the same results given similar access to data, to the tools, to the algorithms? And Edward Raff produced this really nice study not too long ago, trying to reproduce 250 some papers from the machine learning community and really quantifying on the right side which properties were most predictive of reproducibility. And so looking at all of these different characteristics, and he was going based on the paper, but in some case he had access to pseudocode or code. And so he found that significant factors that achieve this were, the availability of the pseudocode, the specification of hyperparameters, the readability of the work itself, the amount of compute that was needed. Also, the topic of the work had quite an influence. Some areas, sub-areas of machine learning are easier to reproduce than others. He came out with a score of a roughly 63% of papers reproducible. If you look at the detail on the right, you also see that, the communication with the authors, the author reply over here was quite significant predictor. So really, this mindset that through collaboration we can improve our ability to reproduce research is also, I think, an important finding of this work and one to keep in mind in our own contributions. So this is an interesting, I encourage you to spend some time reading a little bit more about this study, especially if you're engaging in experimental work. I think there's a lot of insight into how to do this better. Thinking in my own community, in my own literature, giving you a taste of what's the number of reinforcement learning papers we've seen in the last 25 years. If I wanted to do a very thorough reproducibility study of the field, there's been a huge growth and large amount of papers published every year, upwards of 20,000 in the last couple of years. That makes this quite challenging. And so a few years ago, we entered into trying to do a reproducibility study, but of a much smaller set of works, which I'll describe briefly in a minute. What I want to draw your attention to is a distinction. In this case, I'm talking about reproducibility of one particular piece of work result. But where I started in this talk was really more a notion of generalizability. So what can we say when we've had some preliminary results from simulation or models that are well understood and used in the literature? We transfer these ideas to animal models and eventually transfer these ideas to real world systems. And in that case, the conditions change significantly. The number of data that is available in most reinforcement learning studies and simulations on the order of perhaps millions of samples. In contrast, we have a few hundred samples or maybe a few thousand if we're lucky on the animal side. So I just want to call out this difference in terms of practically what we want to achieve is something closer to this generalization. But for the next few minutes, I'll focus more on the very specific case of reproducibility. And so this is a rough taxonomy that has been used across the community. It's not the only one. There's still a little bit of disagreement, but the taxonomy I've adopted in my own work and that of my colleagues is really to use the word reproducible when we're talking about using the same code, the same data. Replicable, allowing some differences of data set, robust, allowing some differences of implementation. And what we're all aiming for in the longer term is this notion of generalizable results, where even if you perturb the data, the code, the analysis, you still have essentially robust findings. So going back to the study we did specifically on reinforcement learning, we focused on the case of gradient-based algorithm. Both because they tend to be quite useful for many practical applications, whether it's in robotics, even in our own neuroscience work, and also because there's been a lot of activity in this field, a lot of people building on this work. And so we started with 4 canonical algorithms, picking them because they were used quite widely in the field, and trying to test, what's the reproducibility of these findings, and where do we see some gaps. And so we ran a first experiment looking at these 4 algorithms on a simple Mojoko task. This is a pretty classic control problem where this little device here, which we call the half cheetah, because it's sort of a lateral cut on what seems like a very cartoon version of a live animal cheetah, has to be trained to run very fast. And so when you do that with these 4 algorithms, you get results that indicate that the red algorithm is perhaps better than the others on this specific task. And so if I was to stop here and read this result from the literature and then transpose this to my neurostimulation or other applications, I might be tempted to say, great, red is the best algorithm. Let's run with it. It's the newest, best, shiniest algorithm. In this case, we tried a few other tasks, and we're not the only one. It's quite standard in the literature to try a few tasks to try to really stretch our results. What's perhaps surprising here is the degree to which there's inconsistencies in the results. So Hopper is a slightly different task, and we also tried the swimmer environment. They all use the same underlying physics engine in terms of controlling the movements, and what changes is the physiognomy of the particular device that has to be controlled, and what's the behavior you want to see. So this one runs, this one hops, but roughly the physics are the same underneath it. And what you see is the red algorithm, which performs so well for running, seems to not be able to learn how to hop or how to swim. Now that's a little bit surprising because you would expect, this is the same rough physics, it's the same it's just an optimization algorithm to some degree. The space is the same, the types of actions is the same. Yet we see here the red algorithm perform really poorly. Blue suddenly becomes much better, which was the worst one before. On swimmer, blue's the best, but with much higher variance. And so the inconsistency between these results, even within a very narrow class of dynamics, is perhaps what's most surprising. All of this work was done with out-of-the-box code packages, not necessarily our own implementation, because we were looking at issues of reproducibility. And so we thought maybe we picked, the wrong packages for doing that. You tried to go with the original authors, but, we tried a few other packages. For the TRPO, which is one of them, we saw quite a bit of difference between different implementation, but it's not just TRPO. DDPG and the other ones also saw quite a bit of differences between the different implementations. Now, this is not completely surprising, and to some degree, we understand where these differences stem from, but it takes some digging to understand that quite well. So one of the difference is due to hyperparameter configuration, right? Depending how you change the network, the structure of the policy network, you get different results. Depending how you change the activation function that is used in each of the neurons of your neural network, you get different function. If you go a little bit deeper, if we look at scaling the reward, which is quite a common transformation in reinforcement learning, that changes things. Whether or not you apply layer normalization also makes a difference. And in fact, the interaction between the scaling of the reward and the normalization of the layer actually has a further effect. So it can become quite tricky to know how much am I supposed to spend tweaking these hyperparameters. That's like the usually way my grad students will phrase the question. The other side of it is, how much data do I need to collect when I'm doing a real world application to make sure that I get the amount of knowledge I need to develop the best system? And now you see a little bit why in doing some of our earlier work, we use methods like random forest, which have very few hyperparameters and are very stable compared to some of, even at the time, were some of the more modern and, in the literature touted as being the more high performing methods. When doing deep learning, of course, there's many sources of experimental variation, and depending on how you set this up, you'll get, of course, a lot of difference in your results. We've also done a bit of a survey of our own within the reinforcement learning literature, trying to figure out who is being clear about all of these parameters, who's been transparent about this. What we're seeing is that, all the papers we selected had some experiments, and most use neural networks. And so that was a bit the inclusion criteria, in a sense, for this quick study. And this is something we did with a small group of students. It would probably need to be redone at larger scale, but it gives you a sense of where the field was at least 2 years ago in this respect. Most of the papers described the algorithms and their hyperparameters. So for the algorithm they were proposing, they had that level of detail. The baselines they were comparing to, it wasn't always clear what hyperparameters had been used to generate the result in the study. We had about 55% of papers at this time that included code. The method for choosing the hyperparameters was specified in only about 20% of papers. About 10% included some evaluation on a holdout test set, and then explicit significance testing with a definition of how this was done was present only in about 5% of papers. So I wouldn't take this as, ground truth, given the relatively small sample set we looked at to do that, but really to give you a taste and an indication of some of the gaps in terms of scientific reporting in the literature. Moving forward, I've been talking about this topic now for a couple of years, and some people are interpreting this as, we should all give up on reinforcement learning as a sub area of machine learning. It's completely rotten, and you can't trust anything that's in any of these papers. I do hope that is not the message you come away from. What I'm really going back to is, this inspiration from Richard Feynman is that, we shouldn't be fooling ourselves as a community of researchers. And we should really be applying a high level of scrutiny to the work that we do, our own and that of our colleagues, but in a spirit of collaboration and co-creation to really increase our standards. So machine learning systems are complex, reinforcement learning is complex, running a lot of experiments with deep learning is complex, but it's also not rocket science, and many other complex systems have been derived over the years. And so one of the things we've done is draw inspiration from systems and processes and tools that have been introduced in those other communities and see if we can translate this to our own work. Back in 2019, we introduced the ML reproducibility checklist as a really practical memory aid to remember all of the components that should be included in the paper. And in many ways, the elements that you find on this checklist are inspired by the gaps that we had seen in the literature. And so there's a block of questions. And if you submitted a paper recently at a major machine learning conference, you may have been invited to provide answers to these questions. There's a block of questions about the models and algorithms you present. There's a bunch of questions about the theoretical claims that are in your paper. I will be the first to tell you that there's very, very few questions on that side. So if someone who does do a lot of theory work would have some suggestions of how we might want to be a little bit more explicit about the expectation on that, I would welcome those suggestions. There's a number of questions on the data sets that are used, whether any data was excluded, how the train test split were done, and so on. There's a number of questions specifically related to code artifacts, which are now often submitted. And finally, the questions that apply specifically to experimental results and go into some of the features that I've been describing recently. It's interesting to note that in deriving some of these questions, we actually tried to look at some of the different features and really ground this in observations from across the field. So specifically for the questions related to code, and the reason we include these specific elements is from a secondary study we did looking at a large number of papers on, GitHub repositories, and seeing, what's the correlation between certain features of a GitHub repository. And each of the ticks, I talk about 5 ticks, correspond to one of the questions that are on the checklist from the previous slide. So, the GitHub repositories that had all 5 of these ticks had, in general, a median of 196 GitHub star compared to 1.5. So you really see a large gap, and you really see the increase in number of ticks when you really go that extra step. Most of these are not difficult. This is not the difficult part of science and research, really. This is the part about doing good bookkeeping, but really seeing the impact of that once you share your work in the public space. So here's a quick summary of what's new since 2018 across the machine learning community. I have to say, since I've started talking about this, and I'm not the only one, there's been others also in the community has been incredibly welcoming of these ideas and keen to try together to improve on some of this. So beyond some of the code submission policy, we've seen in the fall, the archive platform integrate a specific tab for people to submit code and a way to share that with Papers with Code, which does leaderboards and things like that. We've seen a lot of tooling being proposed to encapsulate the research artifacts in a way that makes them shareable and more reproducible. We've seen a reproducibility challenge allow people to take on the reproducibility of papers published at 7 major conferences. as well as journal issues featuring reproducibility reports. So overall, there's really a sense of experimenting with these tools and processes to support the community through that change, which I'm personally very, very excited about. That being said, going back to the work that I also deeply care about on the more scientific front, I don't know that all of these tools and structure is going to help me make that gap to feeling that I have a high confidence solution for treating patients with epilepsy. And so let me talk about a couple other directions that I think are interesting to consider in that direction. The first one, and I'll ground this a bit for those of you who work less in healthcare, in this notion that when you're doing AI for healthcare, one of the important things to consider is what's the level of autonomy that you're putting into the system. And this notion of these levels of autonomy is actually used a lot in self-driving vehicles. The auto industry has done a lot of thinking about that, and you will hear about it if you read this literature or follow that technology progress. In AI for healthcare, we've defined with some colleagues in the healthcare space 4 levels. The first one is when AI is used to sort of enhance human perception or monitor ongoing information. That already captures a lot of the machines and devices that are present in our hospitals. The second level is when the AI is used to actually make predictions or make diagnoses. And this is where right now there's a lot of activity on machine learning on that second level. Number 3, the system provides treatment recommendations. So you can think of a doctor assistant software that would not only make a prediction, but link that prediction to a treatment recommendation. But the doctor is still there in the loop to decide whether to apply the recommendation or not, factor in their broader knowledge. Level number 4, the system is applying the treatment directly. And when we're talking about neurostimulation, this is the case we're talking about. The reason we need to move to number 4 here is because the time scale at which the decisions have to be made is very small. And so you can't have a human in the loop when you're making sub-second decisions. And so depending on the constraints of your application, you may be able to find yourself at different levels of this. It also implies that there's different levels at which humans are able to come into the decision, either for supervision or for intervention themselves. And so for these sort of level 4 autonomy systems, such as this one, there's a much higher burden of responsibility. In this case, there's also all sorts of ways this could go wrong, right? This is just genuinely a set of technical challenges that we have to solve before I feel confident about their solution. Some of them have to do with the non-ID nature of our data, the non-stationary of it over time. Some of it is really figuring out how do we learn good representations. And some of it is about how do we do exploration in vivo when we don't have a priori on the good policy class. And so let me focus specifically on that last one. I would love to, tell you much more about all of these, but specifically on the question of safety guarantees and how do we start thinking of these problems. And I don't honestly am going to give you any solutions to this today. I'm really going to give you a taste for how we're thinking of these problems. And so if we start thinking of this notion of how do you get safety guarantees into RL system, clearly this is going to be crucial for these level 4 autonomy system. We do have frameworks for this, right? We have this notion of constrained MDPs. So it's a standard MDP, state, action, transition, reward. In addition to that, sorry about my notation, I changed at some point, C and D are the same thing. Capital C, capital D, small d, same thing. So C is the cost function, and it's applied as a constraint onto the system. And C0 is sort of your total budget for breaking that constraint. And so the goal of this framework is to find a feasible policy that maximizes the cumulative reward with respect to the cumulative cost constraint. So, it's a nice framework for doing that. It's been tried in a few cases. We've worked with some safe policy iteration methods to do that, and developed in some of our recent work a method to look at the future reward, but also the expected cost incur, and have sort of this forward and backward value function working together at any time point, you can actually frame a nice optimization problem where you're still trying to optimize the standard forward value function as you would in RL, but you're looking at the constraint in terms of the difference between the forward reward, the cost incurred, the estimate of the cost at this state, and your cost constraint. And then there, you can leverage standard optimization tool to solve this constraint optimization problem. One of the challenges in doing that, and I realize I'm giving you just a taste of that methodology, I invite you to read the paper, but one of the challenge we see is, in this case, the blue is the safe version, whereas red is the unconstrained policy. This is on a simple grid world. You see that there's a gap in performance. You see that gap, right? Red does better than blue in terms of the reward. But on the safety constraint, we're able to respect our safety constraint versus the unconstrained method. And green is a different safety method that was in the literature based on Lyapunov constraints. So the finding is, of course, you can control safety, but there's a trade-off between performance and safety. This is not surprising per se, but it opens up a lot of questions about how do we set ourselves up for answering these questions of how to trade this off. Going beyond this, I've talked today about exploration. How do you achieve learning with small amount of data? I've talked today about exploitation, how to achieve high performance in problems. I've talked a little bit, just enough of a taste on safety. But then there's all these other properties that actually we care a lot about before taking these applications into the real world. Security, how do we make sure that the system we develop can't be abused? That someone with their smartphone can't go in and interfere with my neurostimulation device as it's delivering electrical current to my brain. How do we ensure that we avoid biases as we build those systems? Perhaps less relevant in neurostimulation, but most definitely relevant in a lot of other applications, for example, in recommendation systems. How do we make sure that we preserve privacy? And what does that mean in different applications? And finally, this notion of transparency, interpretability, for example, in RL, having a policy that humans can understand. So if I think of level 3 autonomy for my AI system, where there's a collaboration between the human, and the machine that's going to recommend a treatment, but the human will apply it. How do I think about transparency in this framework? And so assuming these are all fundamental properties of RL systems that are important, there's also a good question of how do we establish the trade-offs on this? And the reality is, if I look in the literature, I've showed you the 20,000 papers we have on RL over the last year, and similarly for previous years. 99.9% of them talk to me about the trade-off between exploration and exploitation. And it's incredibly important. Learning efficiency is incredibly important to our system, and I'm the first one to believe in it. I work in small data systems and I want good performance. But I think there's a large gap to talk about all the other trade-offs in terms of these properties. And so one of the message I hope we come out of today is perhaps an invitation for people in this community to think more deeply about some of these questions. This is my very crude cartoon version of what's going on, but there's a lot of work on exploitation, just exploitation on its own, quite a bit of work on exploration and exploitation, and maybe some work on some of these features independently. But all of this other space, and this should not be two-dimensional, this should be, of course, this multi-dimensional space. How do we think of providing guarantees, of analyzing our system, of even framing the problem, of the trade-offs and the compromises that we need to make between all of these different characteristics is going to be crucial to our ability to effectively deploy RL systems. And here, it's not just RL system, but in RL, it's particularly acute because we have been so laser focused on exploration versus exploitation that we've really failed to come out of that dichotomy. And I hope that that we do embrace the full complexity and rise to the challenge of providing better solutions and better trade-offs for all of these other important characteristics of our RL system. The last one I'll add is perhaps most importantly will not just be to have static trade-offs between these different quantities, but allow the user some level of controllability between these different characteristics, and also the ability to understand when you are making trade-offs between these different characteristics. I could go on quite a bit, but in many of these cases, there's a really clear trade-off that can be made if we think, for example, of safety versus privacy. If you keep all of your information private, it's very hard to add a lot of safety layers on top of that information. And so, you know, figuring out how do we set the right trade-offs and characterize them, but then how do we enable users to have that level of understanding and control over the trade-offs that they're making, in particular when their systems are directly affecting them, I think is a really huge opportunity, also responsibility for us as researchers as we move forward. It can be a little bit intimidating to, you know, branch out of this space. Quite frankly, you know, 2 years ago, I had never thought about safety in RL in very concrete terms. I had thought about it in theoretical terms, but like going down to writing down the model and how would we go about solving it, we hadn't done that. We don't have the tools. The good thing is, you know, we are a community of very, very creative researchers. So I'm hopeful we will come out with lots of good solutions to these problems. Just a few final thoughts, and then I'll be glad to take some questions. Of course, I think it's absolutely crucial to have sound experimental methodology, and I will continue to be a champion of reproducibility as long as I have an opportunity to do that. But I hope one thing you get out of today's talk is that that's not sufficient. Even if you're reproducible, even if you're absolutely confident in your results, there's an opportunity to really take on a broader goal than that. Many tools, processes, practices can help us as researchers in being more reproducible. You can use these with your students. It's a good way to bring people into our community. I've been told that using the checklists at conferences like NeurIPS is a good way to set the standards for new reviewers in the community. So I think this can help us all together. But again, not sufficient on its own. Perhaps my third message is an invitation to see your role more broadly, and to not only rise to the challenge of scientific responsibility, but also to engage in terms of the social responsibility that we take on when we deploy these algorithms. I think there's very rich opportunities for empirical and theoretical work on this front. And finally, I remain really convinced that by grounding our research in real world applications is going to help us make the right assumptions and solve the right problems. And as researchers, I think that's quite important. Let me finish by thanking my collaborators. I'm super happy to be here with you today, but there are many students, colleagues who are working very, very hard on this work. Most of the work I described today is done with students at McGill University and our colleagues at Mila and McGill University. Thank you.
Thanks a lot, of course. One of the disadvantages of virtual meetings is we can't hear the loud applause from all the people, but I'm sure that's what people are doing. Thanks for the great talk, Joelle, and we're now all open to questions. Feel free to, I guess everybody can unmute themselves. We don't need to, and just ask away.
So perhaps I can ask a question. Thank you for the amazing talk, Joelle. Amazing as always. So, so this work that you talked about, this deep reinforcement learning that matters paper, that had huge impact on your work for advocating for reproducibility. This has been like really wonderful. And I think this is an excellent service to the field. But I'm just wondering, like, what do you see about like what was the impact of this work? Like what has changed since having published that paper? Of course, like implementing the reproducibility checklist has been a spectacular outcome for sure, but has there been like any measurable progress? Have reinforcement learning algorithms became more stable? Like some people say that, well, it's as unstable as before, nothing works. Some other people say that it's like a lot more stable and robust. I'm just wondering, like, what is your position on this?
I think it's a mix of both. I think, in terms of real stability and reinforcement learning algorithm, we've made some progress, but, maybe 1% of where we would want to be. I think it's still a very long road. I think the inherent nature of the optimization problem is very, very difficult. So I think the number one thing that has changed is our understanding, or, the spirit of investigation that we apply when we look at the results now, as opposed to just taking the results and saying, well, it's going to work, take it out of the box, plug it in, and my job is done, right? That spirit of questioning, understanding, and knowing what questions to ask and what indicators to look at. I think that has changed a lot. Some of the things we've measured, including like the number of papers that are accompanied by code at major conferences, right? It jumped from 50% to about 75% without making it mandatory, with just encouragement to do that. I mean, at a small scale, I see it in the thesis of my own student. This is very, very close, but, they defend their thesis. The early chapters, there's barely any confidence interval, like there's no standard deviation, anything. And over the course of their thesis, you see the methodology get better. This is my own student, so of course I don't have much of a choice to get to the defense. But I have seen it in other labs. I have seen it enter the discourse. Mila is it's a community of 500 students. I don't work with all of them, and I really see that culture of improving the scientific practice is there a lot more. And I think people also appreciate that it's not a trade-off. There's a way to be true to your result and still get a paper in. You don't have to claim that you're better on everything all the time, and that the researchers and the reviewers have a more nuanced understanding of that. But has it made fundamental progress in reinforcement learning stability? I don't think this work has. I think other people have, but at a modest rate.
No, but I think that it has been very important to say those things out loud, coming from the community, coming from people that have been contributing strongly to RL, and the same people speaking up that there's problems. I think that this had wonderful impact. So really,
and it's not just RL, by the way.
Yes, that's right.
Yeah,
right.
A lot of what we say applies to deep learning and more broadly. Generative models are, affected by a lot of the same issues. So.
Yes, and I know that it has also inspired a lot of the work in this renaissance of reinforcement learning theory as well, that you're seeing. A lot of people have seen that there's really a lot of work to be done on that front. So yes, It has been wonderful work, really great.
Thank you.
Thank you.
Hi, can I ask a question?
Yes, go ahead. Introduce yourself, just because I can see the video. Who is speaking?
Oh yeah, it's Lucas Pereira is speaking. I don't have a camera, so I'm not gonna turn on my video. So one of the questions, one of the slides that you presented, Joelle, is about I think one of the results on the survey you did on the papers from the RIPS, ICML, and iClear. One of the things that really got my attention was that there was a percentage rate, 10% of the papers apparently use evaluations on some variation of a holdout test set. Could you kind of like elaborate a little bit on this point? Because it sounded like very alarming for me, because I thought this was like standard basic practice.
Yeah, I will confess, it's a small enough group, right? I can confess this. I don't remember exactly how we tested the criteria when we did the study. So I would have to go back and check exactly our criteria. But what I will say is, in a sense, it's not as bad as it seems, because in reinforcement learning, there is no such notion of like a training set and a testing set that come from the identical distribution. So the way we usually do this, right, is you run the data collection with a particular strategy, you get it set, and then you freeze the policy and you stop your learning, and then you just run the policy in execution mode and you look at what it is. And so most papers did this. Most papers satisfied this bit, but specifically in this case is if you perturb the conditions a bit, can you do the testing? So it's in that sense that we were looking at that, and knowing how RL is brittle, it's actually absolutely essential that people do that. And this is what people are not doing at all. And so it's more in that sense. I would not claim that, you know, papers on supervised learning are not reporting results on test sets. I think that if that was the question, we would have a much, much higher rate of compliance for supervised learning. But RL is a little bit particular that way. And also RL doesn't have yet that great of an argument of, or an agreement in our community of what's the right test set to use. You know, it's good enough to just freeze and run execution, but then we've seen a lot of results that show you can completely memorize the dynamics of the system with a relatively small number of random seeds. So it's not super satisfying. So that's the spirit in which I would take that result.
Okay, thank you. Thank you very much. Still alarming, but a lot better.
Yeah, I'm more alarmed by the low number of people who report significance testing on their results. And in particular, I'm alarmed by the number of people who don't have error bars on their results. And I'm even more alarmed by the number of people who have error bars, but they don't define what the error bars represent. So they put some little shading and it's beautiful when you look at the plot, but you look at the caption and you don't know if those are standard deviation, 1, 2 standard deviation, is it standard error? What level of confidence did you use? And it takes like one line in your caption. And you would be shocked by the number of papers that do this still.
Absolutely. Thank you very much.
You're welcome.
So one question I had is that many of the successes of RL, at least one that I see as an outsider to this area, seem to be coming from big companies, especially DeepMind. And the question is it just the sheer fact that they have many more resources than, say, academia, or is it just also better processes that perhaps they do have some of the secrets to doing that research better that we could learn from, especially as somebody who has bridges the divide between both the corporate world and academia? The question is, what can we perhaps learn? Is there, and how to best perhaps collaborate in this space?
I have a few hypotheses, and before I jump in, let me mention one other project I consider a beautiful demonstration of RL in the real world that is different. And this is some of the work that Mark Belmar and Pablo Castro and some of their friends have done recently on Project Loon, really taking RL to stabilize these balloons floating in air. And the reason I bring it up is that project wasn't done. I mean, they built a simulator to do it, but it wasn't, necessarily based from an initial simulator. You can't write the rules in a compact way. So we're starting to really break out of this space of simulator. And I think the result is really quite impressive, really, really beautiful work. And not by my own company, so I can say it, but still by a big company. So it goes a little bit to your question, right? Like, what's the ability to do this kind of work? To some degree, I think it is a question of resources to be able to take on these really challenging projects, whether it's the AlphaGo, the Project Loon. But the poker player, which I pointed out earlier, this is work done by Noam Brown, Thomas Sanholm at CMU during Noam's PhD. So, and it's one example, but Michael Bowling at University of Alberta has also done beautiful work on poker. So it can be done in academia. The advantage of doing an industry, of course, these days is a huge computation advantage on the accessibility to the servers that you get. There's a sense of really also, putting together a team with a large number of more senior researchers, engineers to do the work. there's also the ability to be ambitious over a longer period of time than in a PhD. And really, you know, in a PhD, you're sort of satisfying certain constraints of that education system, but it's a privilege to not have those constraints imposed on you and allow you to be more ambitious in taking on some of these projects, even sort of trying to shoot for these bigger projects. So I think it's a combination of factors that make it easier to do it in companies. But I would say it's still possible to do in universities, and on a much smaller scale. When I did the work on epilepsy, almost, you know, we started this almost a decade ago now. At the time, everyone was telling me, like, you can't do RL in practice, like it's just not ready to be done in practice. And to some degree, it's just the mindset to want to do it that people need to have. And that mindset you can have either in academia or in industry. It's really quite at an individual level that you have to cultivate that appetite for trying something that no one has done before.
Well, thank you. And is there maybe some opportunity to kind of, or how one in collaboration between in this space that sort of, okay, we still have perhaps some strength and some advantages to academia, and of course with maybe fewer resources, but
there's a lot of it
still in academia.
Yeah. There's a lot of advantage to it. I think sometimes you have to be smart about what work you do where and when, and especially for people who have more theoretical work in mind. I think or at least I'm less familiar about what might be the advantage of doing in academia versus industry. If anything, I think you might have more freedom on the academic side to do it. I will say, though, to your point about collaboration, you know, I think it's still worth doing strong theoretical work inside industry, because it means that people who have a very strong theoretical expertise and mindset see from up close real practical problems and can help solve them. And the level of, you know, privilege you get in viewing those problems when you're inside the company is different than when you're outside of them. But I think there's a lot of models of collaboration. You know, at FAIR, we're really committed to open science and collaboration and so on. And we sort of set the conditions that we can do this work in collaboration with students, with faculty members. We're not unique in that way. Other research industry labs do it also. I mean, for me, FAIR has a very high level of commitment to open science in particular, which I care a lot about. But there's many of these companies that allow visiting researchers, postdocs, student internships, and so on, that let you get a taste of both, as well as the ability to sort of take advantage of both sides.
Thank you, Joelle. Any more questions?
Hi, I had a quick question. At the end, there was like this matrix with like safety, exploration, exploitation, and the way it was arranged kind of suggested like a hierarchy. Was that intentional? Am I reading too much into it?
Let me just point out for the rest of people here that Philip is actually one of the co-authors on the work on safety that I presented today. So glad to see you here, but I want to recognize for everyone with us that you are a strong contributor to that work. Whether there's an intent to the hierarchy, I mean, there's not a very deep intent to the hierarchy. Maybe it's like in terms of how much I've thought about each of them, and I'm transposing that to, I think, maybe how much the community has thought between each of them. And so in that sense, that's a little bit the gradation that is there, but it's not much deeper than that at this stage. I think what I was most trying to convey is the trade-offs happen all over the place. It's not just exploration, exploitation, which of course is the classic trade-off, but for researchers looking for open problems, like this is a really wide open space, and it's not two-dimensional, it's the full 7-dimension or so. And so it's incredible space compared to, you know, we talk about exploration, but we've been exploring so narrowly compared to what we can be doing. So that's exciting.
Thanks.
There may be some low dimensional manifold that's more interesting than like the whole space. I leave it to someone to propose something.
question. So about like controllability, like one of the things that you mentioned, like allowing users to control and understand like the trade-offs between like different properties. Like I'm curious, like how much power do you assign the users to have this control so that they probably don't choose like things selfishly, like without considering maybe other factors?
That's a tough one. I don't know how to do it yet. And I've talked to a lot of experts in the medical field who talk about preference elicitation amongst patients. And the doctors have talked about this, have thought about this a lot, even in choosing treatment option, right? Someone who suffers from a disease, you know, there's a trade-off between having a very aggressive treatment that's really going to reduce your quality of life, having a milder treatment that's going to keep more quality of life. You don't know, there's a lot of uncertainty about the outcomes. So enabling people to make those choices is very difficult. I don't know that I have the answers right now. And if I look at the other side of my work, where, you know, I'm working in industry, and I see some of the systems that, you know, users have to read through in terms of like setting their preferences for their, you know, profile on a social network or another, and you have that level of controllability, but are you actually using it? Are you using it in a way that's consistent with your core values? You know, the ease of doing that, I think, is still very, very difficult. I think to make progress on this question, we need to work with experts from other fields, people who come from user research, from psychology, people who come from economics and social choice theory, and really try to get a deeper understanding of this. So right now, I think I'm still at the phase of calling out to the wide open field rather than proposing solutions. And we'll probably have to start more modestly in smaller problems where it's more, you know, two-dimensional trade-offs. And there's nice work, of course, on an RL with multiple dimensions of the reward function, multiple criteria, and so on, that looks at that.
Thank you.
You're welcome.
Sounds like there are no more questions. Let's thank again to Joelle and for the wonderful talk and the Q&A session. Hope you will stick around. If not, we all know how to reach you.
Yes, please do. Don't hesitate. It was a pleasure to be with you here today. Enjoy the rest of the conference.
Thank you. Thank you.
Thanks very much.